In this demo, we will begin building the grid for the shallow water model example, and that we will use to look at solution of linear waves such as the inertial gravity waves, Kelvin waves, Rossby waves, and topographic waves. Now, so I'm logged in the cluster, and this is my main directory. We will go in the ROMS example directory, and once we go there, there's a new directory called shallow 2D, which is where I'm going to run my shallow water simulations. If I do an ls, here I have the usual directory structure with the bin, input, matlib, the output directory, and the scripts directory. So we're going to go in the matlib directory, and we're going to begin building this grid. Now first, before starting to build the grid, let's see what type of grid we'd like to build. And so here I plotted one already. So we're going to build a rectangular grid that has dimension of 10,000 kilometers in the x direction and about 3,000 kilometers in the y direction. It's going to have closed boundary conditions, and it's going to have an average resolution of about 50 kilometers. Okay, so this is kind of an analytical grid that we're going to build. So to do that, let's go back to our window here. In the MATLAB directory, there's a script called sw create grid, okay, that I prepared so that you can see how to build such a grid. So we will begin in the script by defining some parameters of the grid, in this case the resolution, and this is in meters, so it would be 50,000 meters, which is 50 kilometers. Then we'll have some conversion factors like kilometers to meter, 1,000, and seconds to day. Then we're going to say that the overall length in the delta x direction and delta y, meaning the dimensions of the domain in the two directions, is going to be 10,000 kilometers, and we'll convert this into meters. We're going to define a file name for the grid, since we're building one, and we're going to put it in the usual directory, which is the input directory. So it's going to be one directory up into the input. And we're going to call this application shallow 2D dash grid. Then we're going to set some other parameters of the problem. We're going to say that the ocean is going to be flat at first, and it's going to have a mean depth of about 200 meters. Because we are doing geophysical fluids, and we want a rotation rate, we're going to say that the rotation rate is approximately the one that we have at 30 degrees north. So we're going to set a reference latitude. Other needed parameters here for us are the Earth radius and the gravity, so we're going to put it here. We're going to define the rotation rate of the Earth, the Coriolis parameters, the beta parameters. These are all things that you can look up in the book. We're also going to compute the average phase speed of the gravity waves in such a configuration, which is g8, the square root of gh. The Rossby external deformation radius, which is the phase speed of the gravity waves divided by the Coriolis parameter, and also the phase speed of long Rossby waves, topographic waves, and so forth. Here, this is a portion of the script that just prints out some useful information. For example, it plots out the time it takes for gravity waves to cross our domain, and this is computed over here by taking the length of the domain, dividing by the phase speed, and then converting it into days. And these are useful information when you set up your problem, and as we will see shortly, because you have to decide the time step, and so you want to know how fast the gravity waves are propagating, because you need to resolve them. So having said that, then we can go on and build the grid here. The first thing that we do is we have to define the number of points in the x direction and y direction, which is going to be the total length of the domain divided by delta x, which is the spacing. And once we have this information, then we can use the script rgrd_ana_grid, which we've used before. And the inputs are the spatial resolution in the x and y direction, the number of points, and then the name of the file name. At that point, then, once you create the grid, you're going to configure this grid in the shallow in the RNT toolbox, and I already configured one, and then we can load this grid using the grd grid load command. So actually, let's try to execute this first part. So I'm going to select all this stuff here, and I'm going to go in my MATLAB directory, and I'm just going to paste it. Okay, so execute that first part. Sorry, where is the... Okay, so we have that. Then we are going to go further down and insert these derived parameters. Okay, and compute these numbers here. Do that. Okay, and so now we can, for example, display the speed of the waves. gravity waves, which is going to be the time for gravity waves to cross the domain is about 2.6 days, so they're extremely fast. We can also do the same for the Rossby waves. And the times for Rossby wave to cross the domain with these parameters are about 15 days, so they're still very fast. And the topographic waves, the way I configure these parameters, it's going to be about 46 days. Now, topographic waves only exist, of course, as they're sloping topography, but so for the moment, these waves would not exist. Okay, so having said that, now let's build the grid. So we define the 2 dimensions here, and then we just build the grid. So now I use the script, our GRD ana grid. Okay, and now if I do ls./input/shallow 2d-grid.nc, we find that the file is actually there, and we can look at this using the ncdump command. And you can see that, you know, we have all our quantities. Now, of course, this file has we have to define still the topography in this file, meaning the bathymetry. So now we're going to go further down here, and we're going to open the topography file and set the f parameter to be equal to f naught, and the depth to be equal to h. Okay, so which is a mean depth of 200 meters, as we said before. So we're going to do this, and we're going to execute this again. Okay. Now in the future example, if this particular example here is basically has a constant f, so it's f-plane approximation, and it has a flat topography. So in this type of configuration, you can resolve in this shallow water model, you can resolve basically inertial gravity waves, and you can also resolve Kelvin waves. However, because f is a constant, you won't have any Rossby waves, and because the topography is also not sloping, you will not have any topographic waves. So in the other examples, as we'll show later, we're going to actually change the f parameter to be an f naught plus a beta term, so that will allow the propagation of Rossby waves as well. And we're also going to have an example in which h is going to be equal to some flat topography h plus a sloping component, which is associated with this alpha, which is the slope dh dy, and this would be a slope in the y direction. Okay, so this is all for building the grid.